Let me introduce the PEDAS-Foundation program. PEDAS-Foundation is a design tool for foundation where, when equipment and load information is entered, the program automatically designs pedestals and footings accordingly. At the top menu under File, you'll find options like New, Open, and Save. These are used to save your current work or open previously saved files. Under the General tab, the Grid Settings menu allows you to input grid information related to the structure. I'll explain this in more detail later on. The Load Case and Combination menu lets you define and manage load cases and load combinations used in PEDAS-Foundations. Users can create new load cases, add combinations, and manage them as needed. The For Structure menu is where you can configure safety factors for the structure. The LC Selection menu allows you to set or change which load combinations are applied. The LC mapping is used to import data from an ANL file and match it with the PEDAS load combinations. PEDAS supports 8 types of equipment, starting from vertical vessels. There is also a feature called PEDAS Cloud that lets you import equipment data from other programs. Structure information can be imported from a STAD analysis file, or users can manually define joints and loads within the program. The optimizing function designs the pedestal and footing automatically based on PEDAS-Foundation's rules. The reanalysis feature allows users to rerun the analysis on a foundation at any time, even after it has been previously analyzed. The Design Column Base menu is used for configuring base plates, anchor bolts, and other elements related to structure column bases. It connects the external modules to bring in the necessary data. Once the foundation design is complete, the program generates output documents such as calculation reports, drawings, and material quantities. In the center of the screen, you can see a foundation already created. By right-clicking the output area, you can quickly create a new foundation and view the results immediately. On the left-hand side, the tree view shows the type of equipment or structure associated with each created foundation, allowing you to easily select and review them. Through the Foundation menu, you can group foundation data for easy viewing and management. At the bottom, you will find the Move Equipment function, which lets you move foundation data between different foundation areas. The Equipment Stock function allows you to temporarily delete a foundation by moving it to a recycle bin, and you can restore it later if needed. Below that, you will see detailed information tabs for the foundation, pedestal, and tie-girder. Foundations are automatically grouped based on similar properties. If any of the value differs, the group is automatically broken. On the right-hand side, the Detail panel displays specific information about the selected foundation, including property value. In the Options menu, you'll find the Model Info section where you can enter information about the foundation's position within the model. In the Design Criteria, which is one of the most important settings, you can select the design code and version that will be used for the project. This determines the initial design parameters. Once the design code is selected, you can review and modify related data such as material properties and rebar design standards under the Design Basis section. You can also check and configure soil data and analysis parameter here. For the analysis settings, you can select predefined configurations such as 1A or 2A depending on the type of analysis. Under footing forces, the program offers three analysis methods. Method A, B, and C used during foundation analysis. For block foundations as shown on the screen, shear and moment are calculated based on the edge points or pile locations. We will go over this in more detail later. In the support type section, you can choose between shallow foundations and pile foundations. Shallow foundations allow you to configure options like soil bearing and sliding behavior. For shallow foundations, you can either manually input the soil bearing capacity or define a soil bearing geotable. Once the applicable range is entered, the program uses linear interpolation to calculate the appropriate soil bearing capacity based on foundation size. Under the calculation section, you can choose how to apply soil bearing capacity using the minimum, maximum, or average value based on the logic selected. Alternatively, you can use method 3 mentioned earlier by setting it up as a geotable and applying it again through interpolation. If soil-bearing tension occurs, the program offers three correction methods, method 1, 2, and 3. The correction process follows the guidance provided in the help document. There's also an option to automatically mark the design as NG if the tension area is too small for correction to be applied. Sliding checks are also included as a standard option in the program. For the pile foundations, you can configure basic spacing and cutoff values. Pile grouping is also supported, allowing you to manage multiple piles as a single unit. The program provides three default pile types, but you can freely add and define additional pile types as needed. Pile capacity can be either manually input by the user or automatically calculated by the software. In terms of serviceability, the program supports crack checks, stiffness checks, settlement checks, and buoyancy checks. Note that available checks may vary depending on the selected design code. Rebar design is supported based on the selected design code. If your project uses a code that isn't currently supported, you can request it and we will add the necessary data. You can also modify or add new rebar settings directly within the program. By entering the K value, the system calculates rebar quantities precisely using a bar bending schedule. Currently, the software supports several rebar types. In the rebar arrangement settings, you can configure bar spacing and concrete cover. Concrete cover values can be set separately for bars smaller or larger than 25 mm in diameter. For vertical rebar, you can select the bar type according to your project needs. This setting is directly tied to the bar bending schedule. The same applies to octagonal and hybrid rebar types. You can configure top and middle spacing as needed. With STAAD FEM integration, The foundation can be linked with the STAD solver to import structural analysis results. We'll demonstrate how to run FEM analysis using this integration later on. For special equipment like ring walls or vibrating machine, PEDAS-Foundation provides additional analysis options tailored to their unique behavior. All of this data can be saved and shared through the import and export functions, allowing smooth collaboration with other users. Now, let's go over the optimizing options in PEDAS-Foundation. The optimizing settings allow you to define how the software determines the minimum design values and how optimization is performed during automatic design. For pedestals, the program typically optimizes using rebar sizes ranging from D16 to D29. If you need to use bars larger than D29, which can be difficult to implement in real projects, you can manually define a custom range and the optimizer will adjust accordingly. The same applies to footings. You can set the minimum starting size, control the footings aspect ratio, define the increment steps for each optimization cycle, and specify the rebar spacing. For block foundations, you can configure the rebar spacing and the diameter of the block rebars as well. The default values for HS and HF types can be set based on the structure and equipment type. The minimum pedestal size is defined per equipment type, and if the NC value is small, the program will gradually increase the dimensions to meet the design requirements. In the case of horizontal vessels, the weight distribution between the sliding and the fixed sides can vary, so the optimization options allow you to define this ratio. There is also a setting called the optimizing design ratio, which adjusts the stress utilization level used in rebar calculations. For example, if the software typically designs up to 85% capacity, you can lower that threshold for more conservative design. Now, let's take a look at the foundation detail view. When you select a foundation and double-click or right-click and choose Design Foundation, a detailed design window opens. Here, you can review the foundation shape, dimensions, stability checks, and stress analysis results. For stability checks, you can view the results for each load combination used. Just double-click a result or use the log window on the right to review each case. Sliding and overturning checks are also available in the same panel. If you double-click on a strength check, you'll be able to view calculated shear and moment values. At the bottom, you'll see the rebar layout. The rebar is calculated based on moment values, and you can configure bundling options, bar diameters, and spacing. As you modify spacing or rebar type, the results update instantly. Under the Analysis Criteria tab, you will see whether a strip method was used for analysis. You can also switch to STAD FEM results if you have linked your model with STAD. The current foundation type is set to shallow, but you can change it to pile foundation at any time. You can also switch between spread and block foundation types depending on your needs. In the pedestal settings, you can double-click or right-click to access all related information. You'll find analysis options, dimensions, location data, and rebar settings. If you're using PM interaction analysis, the corresponding results will also be available here. In the Settings for BM tab, you can define options like excavation depth and surface information to help calculate material quantities. Under the Document section, you can configure how this foundation is linked to reports, drawings, or external systems. All linked settings will be applied when exporting document. Now, let's walk through how to create foundations for different equipment types. Start by right-clicking the foundation area and choosing New Foundation at this point. Let's begin with the vertical vessel. This vertical vessel uses BCD dimensions to create a symmetrical foundation. In the LC tab, you'll see one default combination, but you can add more such as empty, operating, test, wind, and seismic. Once you enter the data, the program automatically generates load combinations. You can also input anchor bolt data, and the model will display the anchor positions. Next is the horizontal vessel. This has two support points, a fixed side and a sliding side. You will need to define saddle positions and select the vessel orientation. It also supports both transverse and longitudinal loads. Once the loads are entered, the system distributes them accordingly, taking into account the ratio between fixed and sliding sides. The anchor bolts and plates can be applied either uniformly or individually per sides. Now for the heat exchangers. It is almost identical to the horizontal vessels, except it includes bundle load input as an additional factor. Next is the tank. Tanks are typically large and require special settings. First, select the tank type and input the necessary parameters. If the tank includes a pedestal ring, you'll be prompted to define ring wall properties. When ring wall is enabled, you'll see fields for test and operating heights. The program links the loading height to the input heights, so make sure the values are consistent to avoid internal calculation errors. After everything is set and you click OK, the ring wall will be shown in the model. You can also choose the geometry, 12-sided or 16-sided polygons, and from the Analysis tab, you can access tank-specific load settings. Now, let's talk about the vibrating machine. This foundation defaults to the static type, but if dynamic behavior is required, you can enter dynamic properties for vibration analysis. Loads are handled similarly to other types, but in the design window, you will see additional checks for vibrating related conditions. Next is the package type, which is the most basic foundation. It has no directional components and relies solely on user-entered X and Y shear and moment data. The default is the block foundation type, but you can always switch it to spread type from the design menu. Now, for the multi-point equipment, unlike previous equipment types, which have one or two load points, this one lets you define multiple load points on top of the structure. You can assign different loads to each point, and the system will group them towards the center to complete the design. Let's move on to the pipe sleepers. This foundation type is used when multiple load points exist along a pipe run. Each pipe can have its own load input, and you can even apply anchor forces at specific locations. Once one unit is created, click Pipe Sleeper menu and click Clone, and define how many units to generate and at what spacing. You can also rotate individual units and reposition them freely. If you change one pipe sleeper's parameters and want to keep it separate from the group, use the split or copy functions to isolate it. Finally, visual cues in the tree view show which foundations have anchor loads applied and which don't. This helps you quickly identify what still needs to be configured. Now, let's talk about pit foundations. Currently, PEDAS-Foundation supports single-foot structural models. Multi-foot or extended configurations are in development and will be available in future updates. Now, let's take a look at how to integrate models from STAD. When you run a structural analysis instead, a software generates an ANL file. This file contains joint coordinates, section names, and load combinations. By importing the ANL file into PEDAS-Foundation, you can bring in those joint positions and the corresponding reaction forces. These values are used to automatically build the foundation models based on real analysis results. You can select only the combinations you need and use them to generate one or more foundations. Now, if you're using the user structures, instead of importing from STAD, you can define all the joints, loads, and combinations manually. Doing this from scratch can be a lot of work, so PEDAS provides a shortcut. You can import this data from Excel. Here is how it works. You can export joint and load information from an existing ANL file and open it in Excel, make changes, and then re-import it directly into the user structure. The import includes joint locations, load combinations, and reaction forces. Once everything is imported, the program creates the structure model, and you can proceed to generate foundations just like you would for any equipment. Now, let's go over how to combine or isolate foundations. If you have multiple foundations that are close together and need to be unified, select them and use the combine function at the top left. They will be merged into one foundation. But if you decide later that they should be treated separately again, you can use the isolate function to split them back into individual units. You can also right-click any foundation and switch between pile and shallow types as needed. Next, let's look at how to use tie-girders. In the Combine menu, choose Tie-girder and click Add. You can choose to connect either pedestal to pedestal or footing to footing. For pedestal to pedestal, you can set the start and end points and define an elevation offset. This allows you to control the height of the tie-girder connection between each unit. If you use the footing to footing option, the system will ignore the pedestal geometry and simply connect the footings directly. Now, here's something important to remember. When you connect foundations with tie girders, you can't use strip analysis anymore. In this case, you must switch to STAD FEM analysis. Let's go ahead and walk through that process. Once you start STAD FEM analysis, the program automatically creates a mesh that can be interpreted by the STAD solver. It prepares the foundation geometry and breaks into finite elements. After analysis, the results, like the shear, moment, and support reactions, are imported back into PEDAS. Each value is linked to the corresponding foundation element and used for final design. Now, let's go to the Footing Design tab and click SFD BMD. This will display shear force and bending moment diagrams for the most critical load combinations in your model. These diagrams are also connected directly to the report system, so the most critical values are automatically included in your documentation. Let's now take a look at how to design a custom shaped foundation. By default, when you combine multiple foundations, the result is a standard rectangular shape. To modify that, go into the Design Foundation window. Here you'll see the default rectangular shape under Foundation Shape. Change the shape mode to User Shape. This allows you to fully customize the geometry. You can cut corners, merge extra parts, or even adjust the size by dragging the shape's vertices. Now, when you're working with irregular shapes, we recommend switching the analysis method to StatFEM because strip analysis may not give you accurate results for these types of geometries. To do this, go to the Analysis settings, select StatFEM, and rerun the analysis. PEDAS will now analyze the foundation using the custom shape you have created. In some cases, if the shape is too complex or not ideal, you can use the Modify Geometry tool to reshape the model closer to a proper rectangle. This helps the meshing process and improves analysis stability. Once the analysis is complete, click Save as .std and .anl file. This will generate the STAD-compatible output files that you can open directly in STAD to review the mesh and results if needed. Let's go ahead and save this now. Once saved, open the file in STAD and you will see the fully meshed, analyzed model ready for review. Now, return to PEDAS and click the Finish button. This will import the final STAD results back into the foundation model. All calculated shear forces, bending moments, and reaction forces will be saved and applied to your design. And just like that, the final design results are now fully reflected in your model. Next, I will explain how to use load cases and load combinations. Let's start by creating a new file to walk through the process. Once we create a foundation using the vertical vessel described earlier, we can right-click this and select View Load Combination Value to see the loading information for this equipment joint. By default, the foundation is using a common load combination. This setting is controlled from the top menu under Load Case and Combination for Equipment. In this case, we are using the default common combination. If you'd like to create your own user-defined load combination set, you can do so manually or by copying and pasting from an existing one. You can also use the matrix view on the upper right to select and organize load cases. Then simply input the load factors and the program will automatically generate the corresponding load combinations. You can rename any load combination by editing the report label on the right side. Now let's go back to the foundation we created earlier. Right-click and select Edit Equipment Loading Data. From here, we can switch the load combination to the one we just created. When you return to the View Load Combination Value window, you'll see that the foundation now uses the new load combination. For example, reduced from 21 cases to just 5. To manage load cases, go to the Load Case menu under Predefined Load Cases. You can use only the system-defined cases. Under User-Defined Load Cases, you can freely create your own. Each load case can be categorized by type. Once you have created a new load case, you can add it to any existing load combination set. You can also enter load factors manually or use copy-paste with Excel. Just select a range, copy it into Excel, edit it there, and paste it back into the matrix. This makes editing large sets of data much easier. If you have defined a new structural load manually, there won't be any loading data initially. In this case, go to the Equipment Loading Settings, where you will see the new user-defined structure case added. Click it and manually input the appropriate load data. This updates the combination and applies the new loading configuration to your foundation. You can apply settings individually to each foundation, or you can combine multiple equipment items into a single foundation. When combining, you'll have options such as aligning to the pedestal center, the total size center, or the center of gravity. There is also an option to disable optimization, which allows you to fix the size to either the pedestal or the footing without any automatic adjustments. Once the equipment is combined, the load combination becomes a union of all related data. For example, a vertical vessel that initially had only user-defined loads will now also include the common combinations. If you include a user-defined structure imported from STAD, note that STAD load combinations are defined differently from those in PEDAS-Foundation. As a result, you will need to align or map the two sets of data. To do this, click Combine, and the program will prompt you for mapping information. You can either manually assign load factors to each STAD combination or use the Load Case Mapping tool to automatically align the cases. In this example, we will map up to the empty, operating, and wind load cases. After mapping, run the auto generation feature. The system will analyze the load cases, apply the correct factors, and generate new combinations accordingly. Once this is complete, you can merge the data. This updates the vertical vessel to use the mapped structural load combinations from STAD instead of the original ones defined in PEDAS-Foundation. If you want to change the configuration later, just update the mapping settings. Foundation dimensions can be modified individually, and you can also modify the dimensions of multiple foundations at once. The first method is to design the dimensions of a specific foundation, then copy it. By pasting it to another foundation, only the dimension information is copied. The load information is not copied. If the foundations are the same, they will be grouped together in the foundation list at the bottom. If you double-click the group row or use Edit Foundation to change the dimensions, all dimensions in the group will be updated. Lastly, you can select a foundation and use the Change Property menu to change only specific property values. Foundations display different colors for NG status, instability, strength, and rebar check. Even on the full screen, users can easily identify where NG occurred based on color. The LC selection function allows users to change the check settings of load combinations. You can configure check items for each load combination set, and you can exclude unnecessary load combination checks for each item. For structures, you can set the grid information. Joint information related to the structure is automatically generated, so users only need to enter the related text. This information is automatically linked and shown in reports and DWG files later. You can change the soil elevation of the foundation. In the foundation information screen, go to the top right of the dimension section and edit the finishing elevation to change the soil level. You can raise or lower the soil level. Alternatively, when the Shift Only Soil Elevation option is turned on, you can move the soil level without affecting the foundation dimensions. In this case, you can also set the soil level above the pedestal. By default, the joint center, pedestal center, and footing center are all aligned in foundation design. You can apply eccentricity to the foundation. In the foundation information screen, go to the lower left of the graphic and run the Move Footing menu to move the footing. The pedestal remains fixed, and when the footing is moved, eccentricity is set. When you run the analysis again, the related results are recalculated. The foundation revision function captures a snapshot of the current dimension information. Snapshot information can be linked to reports and DWG files. You can accumulate revision data, compare it with previous revision dimensions, or restore the previous dimensions. Foundation outputs are provided in the form of reports. They include the dimensions used in the design, analysis results, and checklist results. Each chapter includes detailed content, and related reference information is provided in blue text on the right. All formulas and results used for checks are also included. Group reports include multiple related foundations summarized in a summary chapter. Foundations with similar content are grouped together. A detailed report is created for one of them, and the rest of the group is represented as a summary chapter. The content of the report can be added by the user. User-added pages appear with blue titles. The user can edit added contents with the User-Defined Contents tab under the Detail of Content menu. Both text and images can be added, and the entered content is reflected in the report. The header and footer of the report can also be customized. You can check the currently set area with Select Header and Footer Area button. And after editing the content, select the area again and apply it with set header and footer area. The cover sheet can also be modified. Red and blue lines indicate the page boundary. Variable text is linked to foundation information and is automatically updated. For example, title, document number, and revision. These are linked with the report contents in the document tab of the foundation. Foundation DWG outputs include detail, FLP, and PLP. The detail drawing provides the foundation's plan, section, plan reinforcement, section reinforcement, the pedestal design, and the bar bending schedule. FLP is the foundation location plan, which shows the entire foundation layout. PLP is the pile location plan, which shows both foundations and pile locations. All outputs can be generated with AutoCAD and can be saved as DWG files. This is the Foundation BOM report feature. It outputs the basic BOM for the design foundation. For excavation, it includes both the sum of each quantity and the total result across all foundations. The BOM shows overall quantities, summary per foundation, foundation details, and foundation rebar sheets. This explains how to configure mixed piles. A mixed pile is when two types of piles are assigned to a single foundation. First, place piles using one pile type. Then, set the secondary pile type. And go to the Pile Edit menu to change specific piles to the secondary type. This explains how to design a single row pile foundation. When piles are arranged in a single row, the moment of inertia of the pile cross-section becomes zero in one direction, making it impossible to calculate the pile reactions. In PEDAS, the set to zero moment option is provided to force the moment in the zero inertia direction to be set to zero, allowing the foundation to be calculated. This option should be used only when the upper moment is very small, and the piles should be arranged after comparing the magnitudes of the upper moment in the x and y directions.